Hi everybody, welcome to the next lecture of aircraft flight mechanics. This is the third time that I'm going to try and record this introduction. Each time I've failed to remember to put the notes behind me. Now that's one of the benefits about doing a live class, is that one of the students would have reminded me immediately. Anyway, let's remember to put those notes behind me now. So here we go, and I'll make myself small. We're going to go through a few things today. We're looking at just a quick review of those airspeeds that were introduced yesterday. I went through them and the derivation of where they come from, and we're going to talk about them in a different order today. We're then going to go through numerical examples, starting with an indicated airspeed, ending up with a true airspeed, and then turning that also into a Mach number. We're going to look finally at the significance of equivalent airspeed, why it's useful and why it's good to be able to speak about equivalent airspeed as an aerospace engineer. It's not typically used by pilots, none of the pilots that I've spoken to, but it's a very useful one to be able to speak about. So, the airspeeds that we spoke about yesterday, we introduced 4 airspeeds, and we can remember these in order by the mnemonic ICE-T. I'll put a bracket G at the end for ground speed, remembering that if we're looking for distance and time calculations, we look at ground speed. Okay, so the airspeeds we've got, the first one is indicated, next one is calibrated, then we've got equivalent, and then we've got true airspeed. So the symbols for these are VI, VC, VE, and just plain old V for true airspeed. Now we can describe these. This is what the airspeed indicator is displaying. I'll say saying there, which is not particularly good English. Calibrated airspeed is VI corrected for installation effects. I'll say installation or position error. So that's where we have an error that's usually in whatever units the airspeed indicator is saying, which will be knots, that we can add on. Equivalent airspeed is then calibrated airspeed that's been corrected for the pressure at altitude. And then true airspeed is VE corrected for the density. Okay, and we introduce the equations that help us learn or go through what each of these is. So we could say here that V is equal to the square root of 7p on rho, and then delta p divided by p plus 1 to the gamma minus 1 on gamma minus 1, all square rooted. Now we're not really going to use this equation. I'm introducing it here because it helps to understand the relationship between these different airspeeds. So what we're actually measuring is this part here, which is the impact pressure. That's the difference between the total and the static that is measured by our pedostatic probe. So these are our different airspeeds, and we can use a simple tool to help us remember the respective magnitude of each of them. So if we draw a sort of square root sign, that helps us remember the magnitude of them. So we have VI here, VC, VE, VT, and then I'm going to put ground speed there. So VI and VC are about the same sort of magnitude. So to get from this one to this one, we add on delta VP. Equivalent airspeed is going to be lower than calibrated airspeed as long as you're flying above sea level. So to go this way, we multiply by the pressure correction factor. And then F is the lookup table based upon the calibrated airspeed and the altitude at which you're flying, or at which the aircraft is flying. To go from VE to VT, we multiply by the square root of minus sigma. Sigma is the density ratio and defined as the density at whatever altitude you're flying at divided by the density at sea level. And then to go from VT to VG, we add on the wind speed in whatever units it's given in, remembering that a tailwind we added on, a headwind we subtract it. Now, at no point in this discussion yet have I mentioned units. And there's a reason why I haven't mentioned them. It's because we don't need them for either of these corrections. Both of these are dimensionless corrections. They're just multipliers that help us scale between whatever units we have. So typically, VI will be given in knots. Okay, knots are a unit of speed that are typically used by airframers and is used all around the world to measure airspeed. So if we've got a VI measured in knots and we've got VP measured in knots, then our answer stays in knots all the way through this process until we get to the end. Okay? So keep it in knots and then convert it at the end would be my advice. And then we've got a conversion from knots to meters per second. 1 knot is equal to 0.5144444 meters per second. Okay? If you can't remember that, you're always going to be sat in front of your computer when you're going through these examples, so you can just Google it. 1 knot in meters per second. Okay? So that's how we convert between these. So these are our corrections, and that's how we convert between these two. So remember, if you write one of these out at the start of the question, if you've got one of these to hand, then you know your respective magnitude. So if you work out an equivalent airspeed, and it's higher than your calibrated airspeed, and your aircraft is at some altitude above sea level, you've done something wrong. And similarly, if you have a true airspeed that's lower than either of these two, you've probably done something wrong in your calculation as well. You've probably forgotten that there's a minus sign here. Okay? So let's go through with a numerical example. I'll give you guys a moment to read that. Actually, you can just pause it and read it as well. So what have we got? We've got an aircraft is at some altitude, so we've been given our altitude. That's our H for this, with an indicated airspeed of 180 knots. So VI is equal to 180 knots, and the ASI has or the airspeed indicator has a position error of 2 knots. So delta VP is equal to 2 knots. We're asked two things. What are the calibrated equivalent and true airspeeds in knots and SI units? So SI units, what are they going to be? Well, they'll be meters per second for us. And then at what Mach number is the aircraft flying? So let's tackle this first one. Tackle this first question to get the ICE-T conversion. So let's write this out. So we're starting with an indicated airspeed of 180 knots, and we're at an altitude of 39,500 feet, and we've got a delta VP of 2 knots. Okay, so the first step we can work out to go from, well no, in fact the very first thing we do is what I said what we should do is write down VI, VC, VE and VT. We're not actually asked for ground speed in this, so we can write it in anyway, and then we can just remember that our corrections are delta VP multiplied by the pressure correction factor multiplied by the square root of 1 over sigma, and then if we were doing it we'd be adding on wind speed, but we're not asked for that in this question. So the first step is to get calibrated airspeed. So indicated airspeed to calibrated airspeed. We're going to do the position error. So VC is equal to VI plus 2 knots. So it's equal to 182 knots. Okay? Not all of the parts of this question are quite so easy, and these questions will get more difficult as they go along, but I'm hoping that you guys can easily add 2 to any number. Now that we've got our VC, so we're here now, let's tick these off. So we had VI, we've got VC. We now want to go from VC to VE, so we need to know the value of the pressure correction factor. Now remember, F is a function of VC and the altitude at which we're flying. So we can look this up, we can look in the table. Let me get the pressure correction table up. So we can use this straight from the notes on the website. So I've got the table up here. So we're looking for 182 knots and altitude of 39,000 feet. So it doesn't exist in here and it doesn't exist here. So we would need to do a two-dimensional interpolation on this table to work out what the F is. Now, I'm not going to go through the two-dimensional interpolation. What I'm going to do instead is I'm going to use the functions that are built into this page. I encourage you guys to go through and just check that you understand what these two-dimensional interpolations are doing. I'm going to do the next one by hand after this, but it's just a little bit easier to use the functions on this table if this page builds and fetches it from my binder in time. Otherwise I might have to do it by hand. Building, oh, we're getting there, okay. I don't know why I'm scrolling around the page. I don't think it makes it do it any faster. If anything, it probably makes it go a little bit slower. But we're thinking about what we need to get. So we're getting this pressure correction factor. So we're looking in this table. We know that it's going to be somewhere. We've got 182, so it's going to be somewhere in between these two columns, and it's going to be somewhere around here. So it's going to be between these values. Let's do this by hand then. And then we can confirm. So we're looking for between these values here. So let's work out those. Let's write out this subset of the table. We've got 175 and 200. Let's make a little bit of space because we're going to put 182 here. And then the altitudes we've got 35,000. I'm going to put 39,500 here and 40,000 here. So the values that we have in the table, we've got 0.974, we've got 0.967, and then on 40,000 we've got 0.966, and then we've got 0.957. And the value that we want is in here. So to get that, we need to either work out this and this, or this and this. So we'll choose to work out these two values first. Okay, and then we'll do an interpolation between those. So let's see what this is. So we're going to do a linear interpolation between these two values here. So that's going to give me the pressure correction value at 35,000 feet and 182 knots is going to be equal to 0. Let's move the table away. There we go. So that's going to be equal to 0.974 plus. Now that's going to be 182 minus 175 divided by 200 minus 175 multiplied by the difference in values there. So 0.967 minus 0.974. So if I put that in my calculator, I get 0.974 plus 182 minus 175 divided by 25 multiplied by 0.967 minus 0.974. That gives me a value of 0.972. I'll present this to more decimal places than I've actually got in the table. So I've got that value here, and I can now work out this one as well. So let's work this one out. This would be the pressure correction value for 40,000 feet and 182 knots. Similarly, that will be 0.966 plus, let's just work out what this is here. This is 182 minus 175 divided by 25. Well, 7 divided by 25. And the difference that we're looking for here is 0.957 minus 0.966. So 0.966 plus 7 divided by 25 multiplied by 0.957 minus 0.966. And that gives us 0.96348. So now we can then interpolate this value here in the center, so we can get the value that would be in the middle of this table, which is the one that we want. So then the pressure correction value for 39,500 and 182 is going to be equal to, let's take this first value here, the lower altitude, that's 0.97204 plus, now we are 4,500 feet above that altitude because we are 39,500 minus 35,000, and then the difference between here and here is 5,000. And then the two values are 0.96348 minus 0.97204. So let's put that all on my calculator. 0.97204 plus 45 divided by 50 multiplied by 0.96348 minus 0.97204. That gives me 0.964336, which again is more decimal places than we need. So let's print that out to 4. Let's say this is 0.9643. Probably should only really give it the same number of decimal places as the table, but I'm going to include an extra one for good luck. Okay, so that's what I got doing it by hand, and I expect you guys to be able to do that as well. Let's just check that that agrees with what the interpolation routine does on the website. So 182 39,500, this is ready. So if I run this now, there we go, 0.96433. Perfect. So that we know that the stuff that's taking place using these fancy pants calculators that are on the website, we know how to do all of these. Okay, so we're pretty happy there. There we go. So now we've got that value. What do we use this? What do we use this for? Let's get rid of the notes from the page. So now that we've got this, we're doing the next step. So CAS to equivalent airspeed, we multiply by F. So then for us, VE is equal to 182 knots, which is our calibrated airspeed, multiplied by that value that we just worked out, which was 0.9643. So 182 multiplied by 0.9643 gives me 175.5026 knots. Now again, I'm leaving more decimal places on here than I'm going to present my final answers to. There we go. So we've got that one, and then we're going to do our next step. So let's remember we've gone here, we've got the equivalent airspeed. Now to get the true airspeed, we need the density value. Okay. So EAS to TAS multiply by sigma to the minus half, where sigma is equal to density at whatever altitude we've got divided by the density at sea level. Now when I went through and did this by hand earlier, I got quite a significantly different answer to what I did in the calculator on the website. So it took me a while to just figure out what the problem was there. So if you follow the notes, the accompanying notes that we have, so which is what we were using for the course last year, you can use the values from either of these atmospheric tables. So we've got values of the US standard atmosphere which is, I've got one in metric, so we've got these horrible units, which is take these, multiply them by 10 to the minus 4, and that's density in slugs per cubic foot. Alternatively, you can get these, divide them by 10, and this gives us density in kilograms per meter cubed. So if you go through and you do these values, then you will end up with a value for sigma that's slightly different for this. Let me just find what I worked it out to be. I'm not going to go through all of these again. So sigma from the table, and that's if you're looking at the PDF notes, the value of sigma that you'll get, if we get the two densities, you'll do a two-dimensional interpolation just as I've done before. You'll end up with 6.021 divided by 23.77. So I'm using those densities in slugs, and I've not bothered to multiply them by 10 to the minus 4. You'll end up with a sigma value of 0.2533, and that's using all of those values from the table. If you're using the accompanying notes on the website and you go and use the sigma calculator, so there's a sigma calculator here, and you can see I've been messing around with this today because it's got the correct altitude in here. If you run it, you get the density ratio out as being 0.2531. Move this down a bit. Okay, so that's the value from the table, and this is the value from the calculator. Now, it took me a little while of chasing around, longer than I'm proud to admit to, of what the issue is here. Now, I went and did some further research about the different sorts of atmospheric tables that we use. When I was an undergraduate, we were taught the International Standard Atmosphere, which is one that's widely used the world around, and I was aware there are different sorts of atmosphere as well, atmospheric models as well. There's the US Standard Atmosphere, and there's the International Civil Aviation Organization atmosphere as well. Now, both of these are ISA extended to go a little bit higher. They're exactly the same thing. So what's used by ambience to get the to get the atmosphere, that is the ICAO atmosphere, the International Civil Aviation Authority. What's used to get these values in the table, that's the US Standard Atmosphere. Now, this table was taken from Tom Yekout's textbook. This one's taking the ICAO atmosphere from the published data. They're actually exactly the same. The issue is that this table has been truncated. So I went through, did a bit of messing around, and have included a bit of extra stuff on the accompanying notes, and I show here where you get these different densities from. So if you get sigma from the table, you'll get 2.2533, which is the value we just worked out. If you use ambience to get the actual proper value of density of an atmosphere from the ISA, ICAO, or the US Standard Atmosphere, they'll all be the same, you'll get this value. If you then use 35,000 and 40,000 feet within any of those models and then interpolate between them, you get a slightly different value. So what this is showing is that the variation of density between those altitudes is not linear, which we know it's not anyway, and how you get those densities will slightly change your density correction factor. So for homework that I give you guys, use the syntax that I've written into this code to make your own density correction factor and use that. Okay? Or if you're in MATLAB, use something very similar using Atmos ISA. Okay, use that one. So just make sure you're aware of that as you go through. Just look through these and check you can understand what's going on there. Okay? It shouldn't affect your answer too much because the actual difference is quite small. But you can see that it's on the third decimal place in these. So we're going to use this value here. Okay, we're going to use the value from the calculator to do our next correction. Okay, so we've got V or VT, sorry, the true airspeed, which is just V without a subscript, is equal to VE multiplied by sigma to the minus a half. So that's going to be equal to 175.5026 knots multiplied by the square root of 1 divided by 0.2531. It was over there. Okay, so this should be getting bigger, which is what we want to see. And we can see that it's going to get bigger by the size of the thing that we're multiplying it by. Okay, so this gives me a value of 348.849 knots. So we've now got the things that we were asked to calculate. We were asked to calculate, in the first step, the calibrated equivalent and true airspeeds in knots and SI units. So we've got those here. Let's summarize these. So VI is what we were given. We then got VC, VE, and V. So let's write these down in knots. So VI was 180, VC was 182, VE 175, and I'm going to present to 1 decimal place, and V was 348.8 in meters per second. So we've got to multiply these by 0.514444. 92.6 93.6. Let's use this value to do the multiplication. 175.5026 times 514444. We get 90.2, let's call it 90.3, and then 348.849 multiplied by knots to meters per second gives us 179.5. Okay, so that's got the different airspeeds that we were asked to get. We can do a quick sense check on each of these. We know these should be the respective magnitudes, so VI and VC should be around about the same, which they are. Equivalent airspeed should be lower, and it should be the lowest of all of them, which it is. And then true airspeed should be higher, and it should be the highest of all of them, which it is. So that's the first part of this question done. We were asked to calculate the different airspeeds, both calibrated equivalent and true airspeeds in knots and SI units. So we've done that. We're now asked at what Mach number the aircraft is flying. So Mach number, we should be happy with saying Mach number is equal to whatever velocity we've got divided by the local speed of sound. Okay, local speed of sound is given by the square root of gamma multiplied by RT. Okay, gamma is the ratio of specific heats. Gamma is equal to 1.4 for dry air. R is equal to 287. I can never remember the decimals on this. 0.058, and the units for that are joules per kilogram Kelvin. And then temperature, this is got to be in Kelvin. Okay, so we need to then work out what the speed of sound is at the altitude that we care about. So if you look up the temperature at 39,000 feet, you will get 216.65 Kelvin. How did I do that? I used ambience to get it. Used ambience, and then the part that I got out, I did dot temperature, and that gives you the temperature in Kelvin. So use that, or you can use the tables to interpolate again. You'll get the same answer. But if we put all of these things in here, we get the speed of sound at that altitude is to 295.07 meters per second. So we've got the speed of sound. How do we get the Mach number? So it's clearly one of these we've got to compare to. We're going to take one of those and divide it by the local speed of sound. So which one do we use? Do we use indicated, calibrated equivalent, or true airspeed? We use true airspeed because true airspeed is a measure of the aircraft or flight vehicle velocity relative to the fluid through which it is moving. So we use that one. Okay, so we use that to go in here. So let's say m is equal to 179.5 divided by 295.07. Equals 0.61. Mach number of 0.61. Okay, and that's a reasonable speed for an aircraft to be flying at. Like I've said, we've got some sense checks for these. So your sense check for these airspeeds is looking at the respective magnitude when we draw out one of these square root signs. Okay, that helps you there. Your sense check for this one should be, is that a sensible Mach number? In the past, have had students go through a question where the question starts talking about something like a Boeing 737 flying. So you're told, it's a jet airliner, and they will quite confidently put down at the end of the question, yep, my Mach number is 51.75230. Nothing else written next to it. Okay, there's a couple of things wrong with that. Well, there's one thing wrong. A typical passenger airline doesn't travel at 51 times the speed of sound. So you should check that. Is this Mach number sensible for the sort of aircraft I'm looking at? If I don't tell you a type of aircraft, this ain't a suitable Mach number for anything. Okay, nothing that I give you in a question is going to be an incredible hypersonic aircraft, so we're not going to be looking at that. Second of all, not only is it wrong, it's very precisely wrong. That's just a ridiculous level of precision to give an answer to that precision anyway. Okay, specifically since we're looking at the tables that have got certain, the F correction factor only has 3 significant figures, so my final answers are in general presented to a similar degree of precision to that, so this would be very wrong. Okay, so that's a numerical example here. There's some more numerical questions in the accompanying notes on the website. I'd like you guys to go through those. We're going to discuss them on Wednesday. We're going to talk a little bit about, I asked you guys to think about this one, so I might just be answering the question for you. So if you haven't thought about this already, I want you to go through and think about it. So equivalent airspeed is really useful to aerospace engineers, and we're going to think about why. And it really comes down to the way that we talk about forces on an aircraft. So the forces that we care about aerodynamically on the aircraft, we've got lift and we've got drag. Now we don't talk about them dimensionally when we're comparing different aircraft or when we're talking about, say, what angle of attack we need to be at to, say, produce a particular lift. So we tend to talk about lift in coefficient form. CL is equal to lift divided by a half rho v squared s. So if we are talking about the lift coefficient and the velocity in here is, because it's got no subscript, that's true airspeed, we then need to know what the density is at that altitude. So if we're using that in our definition of the lift coefficient, then it means that as we vary our altitude for a given amount of lift, our lift coefficient will change. So that can be a little bit confusing. So for a given CL value, or a given lift value, for a given lift value, the CL value changes. And what we're going to introduce in next week's, or in the next lecture that we're looking at, we're going to look at defining something called the stall speed of an aircraft. Now, if we're defining quantities using CL, where we've got the true airspeed as the divisor, then everything's a function of altitude. So our CL that produces a certain lift will change at a different altitude. So if we remember the definition of true airspeed, V is equal to VE multiplied by sigma to the minus a half, which is equal to VE multiplied by the square root of sigma sea level divided by sigma. So we can substitute this into this expression up here. We can replace the V with VE square root of sigma divided by sigma sea level. So we'll say that CL is equal to lift divided by a half rho VE squared rho sea level divided by rho all squared multiplied by S. So that's just equal to the lift divided by a half. These cancel. Rho sea level VE squared S. Now this is really useful for us. Okay, it means that at any altitude, as long as we are talking about a particular equivalent airspeed, then for a given value of lift and a given velocity, we'll have the same CL being produced. Okay, otherwise our CL is going to change with altitude. Okay, so for a given equivalent airspeed, the CL, or the lift coefficient, is the same at all altitudes for a fixed value of lift. And it's all because we've taken what was previously a function of altitude, so remember that rho is a function of altitude, to a constant. Rho sea level is simply 1.225 kilograms per cubic meter. So that's why equivalent airspeed is useful. We're going to deal with this a little bit more when we look at drag versus altitude, and we'll see that actually by talking about when we look at drag versus forward speed, we'll look at when we compare using true airspeed and equivalent airspeed. Equivalent airspeed becomes really useful for that situation. This also means that, see, if we've got for a given equivalent airspeed, the CL is the same at all altitudes for a given value of lift. Now, this means that often pilots don't really talk about CL. So for a pilot, a CL is just a measure of speed, really. So CL is just a measure of speed. So for a given value of dimensional lift, so we know that at a certain dimensional value of lift, that's the maximum the wings can take. And we'll cover this in more detail during load factor, etc. If we are using true airspeed, that fixed maximum value of lift corresponds to different CLs depending on altitude, which means that it corresponds to different speeds based dependent on altitude, which means that the maximum speed of the aircraft changes with altitude. If we're talking about speed in equivalent airspeed, that fixed value of lift corresponds to the same CL at whatever altitude we're at. So then it corresponds to the same equivalent airspeed at any altitude. I'll say load limits expressed in EAS are the same at all altitudes. I'll put in brackets here most of the time. And that's most of the time because I'm talking about load limits where they're just a function of dynamic pressure. So things like if we're looking at the maximum fixed value of lift that a wing can take, that would be included in this. If we're talking about, say, a Mach number limitation, then things get a little bit different and they're not quite the same. But for our purpose, we like equivalent airspeed because it enables us to remove altitude from a lot of things. And particularly, it removes altitude from the relationship between lift and lift coefficient. And that's incredibly useful. So equivalent airspeed isn't the real airspeed the aircraft is flying at, but the way that we can talk about it, we can say equivalent airspeed is the airspeed which, if flown at sea level, would produce the same aerodynamic loads as the current true airspeed at altitude. So if we have an aircraft now, say horrible aircraft I've just drawn. If we've got our aircraft is flying along at a true airspeed, V is equal to, let's say, 200 meters per second. VE might be equal to, say, 150 meters per second because we are at H not equal to 0. So this aircraft is producing a certain amount of lift and a certain amount of drag. So we'll call these L and D. Let's call them L1 and D1. So flying at this altitude, which we don't know what it is, it's just any altitude for this particular aircraft. If we took this aircraft and then flew it down at sea level, so we took this now at H is equal to 0, flying it down at sea level, and this aircraft is flying at the same equivalent airspeed of 150 meters per second. Because we're at sea level, that means that we've got our true airspeed of 150 meters per second. These values would be equal. Okay, so go through this expression, go through this phrase here, go through the company notes, check you understand the significance of what that means, and then we're going to use equivalent airspeed a lot over the next few lectures to try and help us basically remove altitude from some different curves. Okay? So hopefully that's been a good numerical question covering some of the things that we covered in terms of airspeed, and hopefully also you guys have got an appreciation of what equivalent airspeed is. If you don't and you're not quite happy with that, pop a question on Slack. We're going to have a review session on Wednesday, which is like next week for me now, but it's Wednesday during the first week of lectures. So that's going to be available. Details will be announced on Slack. I want you guys to turn up to that even if you're happy with everything, okay? Just pop your head in, say hello, and then we can talk about how this course is going and sort of discuss your expectations for the rest of the term and mine as well. Again, thank you for listening. I'll get on with the next lecture shortly, and I'll see you all whenever I see you all.